Hey everyone, this is our third video on Chapter 2. Remember, Chapter 2 has been focused on acid-base chemistry. Just to give us a quick reminder of what we've talked about so far, we started out talking about the definition of Bronsted-Lowry acids and bases. Remember that an acid is a proton donor, and a base is a proton acceptor. Right, so an acid-base reaction involves the transfer of a proton from an acid to a base. We reminded ourselves of the relationships between acids and bases. We looked at the Ka value. We talked about the pKa value. And we talked about the pH. So remember that the pKa is a constant for a given acid, while the pH is a property of a solution. We then spent quite a bit of time in our last video going through and talking about how structure influences acid-base strength. Right? So we talked about things like electronegativity, atom size, talked about resonance, hybridization, inductive effect, and looked at a number of different trends identifying what properties help stabilize conjugate bases. So remember that an acid that has a stable conjugate base will be a strong acid. An acid that has an unstable conjugate base will be a weak acid. All right, so now we're going to take what we learned last time, and we are going to use it to predict the outcomes of acid-base reactions. Right, so this is going to involve two steps. One, we're just going to predict what the actual reactants and products are. And then the second is that we want to be able to predict for a given acid-base reaction which direction the equilibrium will lie, either toward the products or back toward the reactants. All right, so then we will go on and see how, if we change the pH of a solution, how it changes the structures and physical properties of organic acids and bases. And we're going to just finish off by a quick discussion of Lewis acids and Lewis bases, which is just a different definition of acids and bases. All right, look at some acid-base reactions here. So I had already mentioned that if we just have a pair of reactants and we know that it's going to be an acid-base reaction, then the stronger of the two acids will be the one that donates the proton. So we want to be able to start out giving us with some idea of acid strength. Okay, so let's just write out some pKa values. So the pKa of a carboxylic acid, which is this one on the right, this is a carboxylic acid here. It has one more carbon here than does acetic acid, but we've talked about acetic acid a number of times. So the pKa of a carboxylic acid, we said, is about 5. Okay. This one over here is ammonia, and ammonia has a very high pKa value, so this pKa value is about 36. So clearly this carboxylic acid is going to be the stronger acid, right? So this is going to act as the acid, ammonia will be the base. Right, so from this we know that this proton on the acid is going to be donated over to the ammonia. That's going to give us NH4 plus this O minus. Okay, so this is the ammonium ion, and this is called a carboxylate. Okay, it's the conjugate base of a carboxylic acid. All right. Now, if we look at some pKa values here, the pKa value of an ammonium ion is about 10. And this carboxylate doesn't even have a proton on here anymore, and we know that protons on carbon are not very acidic at all, so we know that this is going to be the conjugate. This is the conjugate base. This is the conjugate acid. Okay, so based upon the pKa's of the reactants, we know which one is going to donate the proton. So to determine which direction the equilibrium will lie, we look at the stronger acid on each side of the equation. All right, so that was this carboxylic acid on the left. And we're going to compare that to the stronger acid, which is ammonium on the right. Okay, so the equilibrium is going to lie away from the strongest acid. So the equilibrium is going to lie to the product side of this reaction because this is the strongest acid over here. Okay? All right, let's look at another example. So in this example, we have an alcohol here. Okay, alcohols have pKa's around 16. And here's acetic acid. So this is another carboxylic acid, which has a pKa of around 5. So clearly the carboxylic acid is the stronger acid here. And so it's going to donate a proton to the alcohol. So this is going to pick up a proton on the oxygen. That's the only atom on the alcohol that has non-bonding electrons that can form a new bond. So we get this called an oxonium ion plus the carboxylate anion. All right. So this oxonium ion, remember that when we have oxygen with a plus charge here, this has a pKa of less than 0. And the carboxylate, just like above, is going to have a very high pKa because it doesn't really have an acidic proton at all. So we compare the pKa's of the acid and the conjugate acid and which side has the stronger acid. So this one is the stronger acid. So in this case, the equilibrium is going to lie back toward the left. All right? All right, one more example. Okay, this is an example of an ammonium ion. In the upper example, this was ammonium. That's ammonium itself. But notice that this is very similar, has a nitrogen with 4 bonds. We've just traded in 2 of the hydrogens for up here for 2 carbon groups down here. So the pKa will be just about the same. Okay, so the pKa here is about 10. Okay, this is called ethoxide. We'll learn these names later. But it's essentially the conjugate base of an alcohol. So this is very basic. It doesn't really have an acidic proton on it. So this one is going to be the acid. This is going to be the base. Right? So we're going to transfer a proton from the ammonium ion. Oops, I wanted to make that blue. So we're going to get this species here plus an alcohol. All right, alcohols have pKa's just like we saw up here, about 16. Amines, just like ammonia up here, would have a pK of about 36. All right, so let's pick out the strong acid. So here is the strongest acid on the left. Here's the stronger acid on the right. So which direction is the equilibrium going to lie? All right, so remember the equilibrium lies away from the strongest acid. So here's the strongest acid. So this equilibrium will lie toward the product side. Okay? So let's just summarize. So of the reactants, the strongest acid has the lowest pKa will donate a proton to the base. All right? Once we figured this out, we can then draw the products, right? So then we look at the strongest acid on the product side, and the reaction equilibrium will lie away from the strongest acid. All right, so the next thing we're going to look at is how pH can affect structure, and once we've changed the structure, how that can affect physical properties as well. All right, so here's another carboxylic acid. Okay, so this so just like acetic acid, it's this portion here, which is the functional group that's going to be going to act as the acid. All right, so we know if we have an acid, that can give off a proton, and it can form its conjugate base. All right, so this would be called the acidic form over here, and this is the basic form. So that means that the acidic form is going to be present at low pH, right? Because that's an acidic medium, and the basic form is going to be prevalent at high pH, so in a basic solution. So let's compare these two structures. Okay, notice the one on the left is neutral. Okay, there's no charge at all. Whereas the one on the right has this minus charge, right? Okay, we could also call this is an anion, right? So it's an ionic species. If we consider their levels of polarity, we would say that the structure that has the charge on it would be more polar. So this is going to be more polar. This is less polar, or more non-polar. And if we think about their solubility in water, we would say that the more polar species would dissolve in water, because water is a very polar solvent. Okay, so the ionic form is more polar, and so this species would be water soluble, because essentially it's going to form a salt. And the carboxylic acid, being neutral with no charges, would be water insoluble. Okay, so we can reverse this. The opposite of being water or soluble is to be what we call organic soluble. So that would be if a molecule can dissolve in some type of organic solvent, like an oil. You know how oil and vinegar separate, or how gasoline will run over the surface of water. So an organic solvent is more like gasoline or kerosene or something very non-polar like that. So we'd say that this is organic soluble, and the carboxylate, the anion one, would be organic insoluble. Okay, so notice that there's an inverse relationship between water solubility and organic solubility. So one of these is organic soluble, then it's going to be organic insoluble. Over here, this is organic insoluble, so it's organic soluble. Okay, so let's look at one example, and then I'm going to show you a practical application of this. All right, so in this case, we have this group is called an amine. It's kind of like ammonia, and it has a non-bonding pair of electrons on the nitrogen. So amines typically act as bases, and they're really one of the most common bases, organic bases. So this is going to act as a base, and so that means it's going to pick up a proton. So it could go to NH3 plus. All right, that would happen if we add H plus. Add H plus, that would take place. Would that take place at a low pH or high pH? Okay, so that would be more apt to take place at a low pH, right? So low pH means there's a high proton ion concentration. Low pH. All right, to go from the ammonium ion over here back to the amine would mean that we have to remove a proton. So what we would do is be to add base. All right, that base would pull off one of these protons and it goes straight back to the amine. All right, so this is going to happen under basic conditions, so at high pH. All right, so let's kind of analyze these two compounds like we did on the last slide. All right, so the amine, is that going to be the acidic form or the basic form? Okay, so this is the basic form. And the ammonium ion is the acidic form, right? It's the one that's protonated. All right, so like we mentioned above, this would be present at high pH, the acidic form at low pH. All right, so now which of these two is neutral in this case? Right, the ammonium ion has a plus charge, and so it's the amine here that's neutral, and this one over here is charged, and this time we have a cation. Okay, so based upon what we learned on the last slide, which of these two compounds do you think would be more water soluble? Okay, so water is a very polar solvent, and so it's going to dissolve the more polar species. All right, so which one is more polar? Okay, the more polar one is going to be the charged species. All right, so this is more polar. So this is the side that would be water soluble. All right, this one is less polar. So this would be water insoluble. All right, and then organic solubility would be just the inverse of those, right? That's what we talked about last time. If the amine is water insoluble, it would be organic soluble. And if the ammonium ion is water soluble, it would be organic insoluble. All right? So, in both of these examples I've just showed you, we can change the ionization state of the acid or base by changing the pH of the solution. All right, so if we have this amine, right, this amine, didn't want to do that. This amine, if we wanted to shift it to the ammonium ion, we just add aqueous acid. So it could be 0.1 molar hydrochloric acid or 1 molar acetic acid or something like that. Some acidic aqueous solution, it would protonate on the nitrogen and it would shift the equilibrium to the right. Once it does that, this species would now become water soluble. If we want to go back to the amine, then we can make that solution basic. Right? We could add some sodium hydroxide to it, raise the pH until it gets at a high pH, and then the equilibrium would go back to the left. All right, now, okay, we can predict which direction it goes if we compare the pH to the pKa value for the acid. All right, so here's the pKa value of the acid would be about 10. All right, so the compound is going to be in its acidic form when the pH is less than the pKa. So as the pH is adjusted downward, making the solution more acidic if it goes much below 10, so to 8 or 7 or 6 or down to 2 in acidic solutions, we're going to be in the ammonium ion form. All right? If we want to go to the amine form over here, we have to make it basic, so the pH has to go above 10. So this has the pH greater than the pKa. All right, so let's look at a practical application of this. And this is going to be something that you're going to utilize if you take a lab class in organic chemistry. It's very practical. So I'm going to have to add in an iode here. And what we're going to do is we're going to look at how we would start to purify the products of a chemical reaction. And we're going to concentrate on a separation step. Okay, in order to do this, we use a special kind of flask. And I'm going to try to use my artistic talents here, which aren't very much. So we have a flask like this. It has what's called a stopcock down here, so it's a valve so we can open this up or close it. All right? What we're going to do is we're going to pour in solvents in here. We're going to pour in 2 layers. So we're going to have an organic and an aqueous layer. All right, so what do you think? If we have an organic layer, something like oil, it could be vegetable oil, could be gasoline, something like that, is that going to be on the top layer or the bottom layer? Right, so we know organic layers typically float on the top. Like if there's an oil spill or something like that. And this will be the water layer on the bottom. All right, so let's think about these 2 compounds that we've been talking about. All right, so let's imagine that we want to separate this carboxylic acid from this amine. Okay? What's going to happen if we add these 2 together? Anything? Well, we have an acid here, right? And we have a base. All right, so what do you think's gonna happen if we mix those 2 together? Well, the acid is going to give up its proton, and it's going to be transferred to the base. So we're just going to get an acid-base reaction here. It's going to give us carboxylate anion plus the ammonium ion. Okay, so if we did just what we did before, we could say that this acid has a pKa of around 5, and this ammonium ion down here, which is the conjugate acid, has a pKa of around 10, right? So this equilibrium would lie away from the strongest acid up here, so the equilibrium would lie to these two compounds here. All right, so now let's add these compounds into this separatory funnel. Okay, where are they going to go? All right, so both of them, because they're both charged, they're both ionic, will both go in the water. Right, they'll both dissolve in the water. So we haven't really been able to separate them yet. We'd like to separate them, so what do we have to do if we want to separate them? Okay, we could do either of two things. All right, we could either make it acidic, so we change the water layer from being neutral to a low pH. And if we do that, we are going to, what's going to happen to the carboxylate right here? If we take this to a low pH, is this its acidic form or basic form? All right, this is the basic form. If we make it to a low pH, it's going to protonate on that oxygen. It'll give the carboxylic acid back. What about this ammonium ion? If we go to lower pH, what's going to happen to it? Essentially nothing. So it's already in its acidic form, so it's going to stay the same. All right, so now we have the carboxylic acid and we have the ammonium ion. Which layer is the carboxylic acid going to go into? All right, it's neutral, so it would go into the organic layer. What about the ammonium ion? Okay, it's ionic, so it's charged. It's going to go into the aqueous layer. All right, so if we make this water layer here acidic and we put our compounds in there, what we do is we put a stopper in the top. Okay, so we put a stopper up here, we plug this up, we shake it up, we put it, set it back upright, and we let the layers separate. And if that water layer is acidic, then, like we said here, this neutral carboxylic acid will go into the top layer, this ionic ammonium ion will go into the bottom layer. And so just by doing this simple procedure, we've separated these two compounds. All right, is there any other way that we could do this? Well, what if instead of making a low pH, we made a high pH? All right, so we, instead of just adding water, we added in 0.1 molar sodium hydroxide. 0.1 molar sodium hydroxide. Okay, so what's going to happen to these compounds? So the carboxylate here is already in its basic form, so it's not going to change at all. It's just going to stay the same. Right? The ammonium ion is in its acidic form. So as we add as we raise the pH, we make it more basic. It's going to give off a proton, and we're going to get the free amine, like this. Okay, so if that water is in a high pH, then the carboxylate is charged, will go in the water. The amine is neutral, would go in the organic. Right? So this is just backwards of what we saw in the previous example. All right, so by manipulating the pH, we can manipulate the ionic state of these acids and bases, and we can then influence their solubilities. Okay, so there's an actual equation that you guys learned in general chemistry that describes this, that we can do calculations with, and you used it to do calculations with buffers and things like that. It's called the, what was that called? It was called the number that tells us Henderson-Hasselhoff, right? Ah, no, that's not right. Not the Hasselhoff. It's called the Henderson-Hassel. All right, so those are the guys. All right, so they came up with this empirical equation. All right, so that's it right here, and we used this to do a buffer calculation. So let's just rearrange this a little bit, and we can put it into a form that gives us some information about what layer these compounds are going to dissolve into. Okay, so what I'm going to do first is I'm going to subtract the pH from both sides. So I'm going to get the pKa minus the pH equals log of the acid concentration over the conjugate base concentration. All right, so now I want to get rid of that log. So I'm going to raise both sides to, well, I'm going to go 10 to the different powers. So I'm going to say 10 to the pKa minus pH power equals now just the concentration of the acid over the concentration of the base. All right? So let's look at three different possibilities here. Let's say first, what if the pKa equals the pH? Okay, in this situation then, if the pH and the pKa are the same, then this number is going to end up being 0, and any number raised to the 0 power, what's that going to give us for the ratio of HA over A? Okay, so that ratio is just going to equal 1. So when the pH equals the pKa, we'll have exactly an equal amount of the acid and its conjugate base. All right. What if the pKa is greater than the pH, or the pH is less than the pKa? So let's take a look at this. So if this number is bigger than, and this is smaller, then we're going to have a positive number here, right? And so 10 to a positive number means that this number is going to be greater than 1. Okay, so if the pH is less than the pKa, then we're going to have more of the acid, right? Because the pH is lower, means it's acidic. And if the pKa is less than the pH, or the pH is greater than the pKa, that means it's more basic, and this ratio is going to be less than 1. It means that we have more of the conjugate base than we have in the acid. Okay? So the main thing is that the anchor point here is the pKa. As the pH goes below the pKa, the solution is acidic, and the compound is going to be in its acidic form. All right, that acidic form can either be neutral or it can be ionic, just depends upon what type of acid or base we have. If you look back, remember that for the carboxylic acid, the acidic form was neutral, but when we used the amine, the acidic form was ionized, right? So we just have to be able to to look at those compounds and figure that out. As the pH goes higher, the solution becomes more basic, and then the compound goes to its basic form. For the carboxylic acid, it went to its carboxylate anion, and that's ionic. And for the amine, it went to the free amine, and that species is neutral, right? So we can just adjust the pH, change the ionization state, and we can change its solubility. All right, pretty cool, huh? All right, so one last thing that we're going to talk about. We're going to give you just a slightly more broad definition of acids and bases, right? We've talked about Lewis acids and Lewis bases. We've talked about Bronsted-Lowry acids and bases where the proton is being transferred, right? So an acid was a proton donor, the base was a proton acceptor. Okay, so for Lewis acids and Lewis bases, we're not talking about protons, but we're going to talk about electrons. All right? So a Lewis acid is going to equal an electron pair acceptor. All right? And a Lewis base is going to be an electron pair donor. Okay, so let's see how this relates to what we've learned before. So here's basic acid-base reaction, right? A proton plus hydroxide, right? So we even did this before where we said, oh, this oxygen has these non-bonding electrons around it, and it can use one of those pairs to form a bond to the proton, okay? So over here, this is the acid over here because it's donating this proton, and this is the base over here because it's accepting a proton, right? But, so we just get water out of this. But if instead of talking about whether this proton is donated or accepted, we look at what's happening to the electrons, right? So in this case, based upon this line here, the acid over here is the electron pair acceptor, right? It's accepting this pair to form the bond, and the base is the electron pair donor. So that base is all, in order to be a base, there has to be a pair of electrons, all right? Okay, so Lewis acid and Lewis base definition can basically encompass all of the Bronsted-Lowry acids and bases, but there's some examples that we describe which go beyond that. All right, so let's take a look at these 4 examples, and we're gonna say whether these are Bronsted-Lowry acid bases or a Lewis acid base reaction. Okay, so let's look at the first reaction. Okay, so up here, what's happening? Right, we have ammonia, and the ammonia is coming over here and taking this proton off. All right, so is this a Bronsted-Lowry acid-base reaction? Yes, we're transferring a proton, right? So it is an acid, it is a Bronsted-Lowry acid-base reaction. What about a Lewis acid-base reaction? Yes, the ammonia is donating a pair of electrons and the proton is accepting. So this is also a Lewis acid-Lewis base reaction. Okay? So what about the next one? What's happening? What's happened in here, right? What's going on here? So look, this in our product, the oxygen now has a bond to the carbon. So we've taken a pair of electrons from this oxygen, and it's been used to form a bond to this carbocation. All right, so is this a Bronsted-Lowry acid-base reaction? No, there's no transfer of any protons, right? And so this is no, it's not a Bronsted-Lowry acid-base reaction. How about a Lewis acid-base reaction? Yes, we have the water donating a pair of electrons. So this is a Lewis base, right? The carbocation is accepting electrons, so this is a Lewis acid. So yes, this is an acid-base reaction if we talk about Lewis acids and Lewis bases. All right, what about the next one? Okay, what's happening in this case? All right, it looks like one of these protons on the oxygen over here has to go on to the other oxygen. Right, so we can take a non-bonding pair of electrons here, forms a bond to this hydrogen, this proton, and these electrons will go back onto the oxygen. So there was one pair of electrons here, there they are, and now a second pair goes on there. Okay, so what about this one? Is it Bronsted-Lowry? Yeah, because we're transferring this proton from one oxygen to the other oxygen. Is it Lewis acid, Lewis base? Sure, because the water is acting as an electron pair donor, so is that a Lewis acid or Lewis base? So this is the Lewis base, and this proton, or this species, is accepting the electrons, so this is also a Lewis acid, Lewis base example. All right, so let's look at just one last example. All right, we know that this oxygen has two pairs of non-bonding electrons. What about boron? Okay, would that have any extra electrons around it? What's the valence of boron? Do you remember? So boron is just to the left in the periodic table of carbon. So it has a valence of 3 electrons, right? So it's picking up an electron from each of the fluorines, so it only has 6 electrons around it, right? So remember, we looked at this before, it would be sp2 hybridized as an empty p orbital. So this non-bonding pair of electrons can be donated to the boron, okay, to form this species over here, right? So this is not Bronsted-Lowry, there's no proton transfers, but it is a Lewis acid, Lewis base reaction, right? Because we have an electron pair donor and we have an electron pair acceptor. All right, so lots of the different reactions that we're going to see throughout this class, we're going to be able to describe in these terms. All right, so is our chapter on acid-base chemistry. Like I said at the beginning of this chapter, I know you've seen some of this before, but this is a very important section because we're going to see these types of reactions over and over again. And so if you can become comfortable with this chemistry, you're going to be comfortable when you see it again later.